Cool. Ready?
There you go.
Cool. So it's my great pleasure to host Jaime for a UI seminar talk here today. I guess I'll just start by giving you guys a bunch of background. So Jaime is an assistant professor of electrical and computer engineering at Princeton University. He directs the Safe Robotics Lab and co-directs Princeton AI for All. His research integrates control systems, game theory, and artificial intelligence to equip robots with transparent safety assurances that users and the public can trust. Before joining Princeton, he was a research scientist at Waymo, where he pioneered new approaches to interaction planning that continue to shape how autonomous vehicles share the road today. He's also the co-founder of Volt Robotics, a startup developing agile delivery robots that work alongside human drivers. Sure, he would love to tell you more about it. He holds an engineering degree from the Polytechnic University of Madrid, and a master's in aeronautics from Cranfield University, and a PhD in EECS from UC Berkeley. His work has also been featured in the Wall Street Journal and Wired, and recognized with the Google Research Scholar Award and the NSF Career Award. And outside of this, Jaime was also my senior thesis advisor while I was still an undergrad at Princeton. He's definitely one of the kindest and the most energetic people I know. I think I always feel amazing every time I finish talking to him. And I think you'll also enjoy this talk a lot. Right, take it away.
Thank you so much, Anoop, for that undeservedly kind introduction. Yes, and thank you all for having me. It's great to be up here in Boston on such a wonderful sunny day. I'm sure this is how it's been all the time for the last few weeks. Yeah, I'm excited to share with you some of the work that my wonderful students and collaborators and I have been doing in Princeton, thinking about ways to really ensure the safety of autonomous systems in a way that is quantifiable and meaningful, and that can really generate trust in the public, in policymakers, and at the end of the day, all of us who have to use these systems and have them integrated as part of our lives. And I know that the range of interests in this group is quite broad. So even though I will be grounding some of the ideas that I'll share in specific types of systems, sometimes walking robots, sometimes autonomous vehicles. I think that the ideas are actually quite general. And towards the end of the talk, I hope to convince you that some of these ideas have merit also in settings beyond the realm of robotics, and in contexts as sort of ethereal and sometimes hard to grasp as the dialogue interaction between human and language model service like ChatGPT. So I'll start off by maybe giving you a little bit of context on why I think that giving meaningful safety guarantees is really important. This is a headline that appeared out in the papers during the year that I spent working at Waymo, and it was kind of concerning news to all of us working on planning and safe decision making, where we found that some person had succeeded in causing a crash. Now I'll show you the footage recorded by the car in a moment, which I'm sure you'll agree that it's not necessarily that the car did anything fundamentally unsafe, but rather that it found itself in quite a tricky and sort of hostile situation that it needs to handle. But we can comment on what goes wrong here, and I think that there's still some room for improvement. So this is the footage recorded by the car. This is the hostile vehicle. You'll see in a moment that they change lanes and immediately slam the brakes, and then the autonomous vehicle rear-ends the car. And so when you look at something like that, when the local police come and take a look at what happened, and of course they get access to the footage, they determine that the other driver is at fault because they are driving recklessly and actively trying to cause a collision, which the autonomous vehicle was ultimately unable to prevent. This kind of rare, extremely rare and sort of corner case behavior is often referred to in the autonomous driving community as the long tail, sort of referring to this distribution of situations that you might encounter you as a self-driving car when you're out there in the world. Now, in some cases you can argue, well, there always will be cases that the autonomous system cannot handle well, and we cannot expect the system to handle absolutely every possible situation that could arise on the road. Especially when it's a tricky situation that you could argue maybe even a human driver might not have been able to succeed in. Now, I wonder, how many of you start agreeing less with what I just said if I tell you that this was actually the driver's third attempt in a row in a span of maybe a minute or two of driving to cause this collision. So turns out that the first two attempts, the autonomous car was successful at preventing collision by slowing down. But I mean, I don't know how many of you are drivers around here, but do you think that if you were driving, there would have been a third opportunity? So probably many of you would have, maybe this would happen the first time, and then you would have kept your distance from, this a driver who is clearly at best not fully in control of their vehicle, and at worst, actually trying to get you in trouble. I think that's some relevant information to keep in mind, because while this is a very extreme case, it's actually not that rare. Road rage is something that I think we've all experienced, hopefully in every case as victims and never as perpetrators. But it is part of what, autonomous systems operating on public roads are going to have to handle. And they need to handle it gracefully, and they certainly need to, adapt quickly when that kind of situation is encountered. So I would argue that this is actually not that far down the sort of hypothesized distribution of driving, whatever that might look like. But there are other cases that are perhaps even more extreme of this. And so let me show you another example. This is from almost 2 years ago, November 2022. It's an autonomous or semi-autonomous system, in particular Tesla Autopilot, that suddenly comes to a complete stop in the middle of the Bay Bridge in the Bay Area, and this is the result, the multi-vehicle pilot. I'll just play the video again to make sure that you all see that there's no apparent hazard on the road that would motivate the vehicle to sort of come to such an abrupt stop. This is referred to at some autonomous driving companies as an emergency stop in lane, which is kind of a really bad situation you don't want to get into frequently. And there's no clear reason here that the autonomous system did this. Seems likely that it was a perception failure. But in any case, it is a little bit concerning when one of these systems makes this kind of mistake, because of course you have to wonder, is this systematic? Is this going to happen again? What kind of assurances can we get? And the state of the sort of regulatory situation, sort of the explanations that are owed by companies, at least legally right now, it's not really quite at the level of other areas, like, for example, aerospace or civil engineering. And so there's probably a long way that we can go. In this case, by the way, there's some good news, which is that soon after this accident happened, Tesla did clarify that this sort of out of the blue failure will not happen very often. So this is where great, but this does sort of motivate something that I think we should keep in mind when deploying autonomous systems, which is that extreme events, rare situations, tricky conditions are not just unpredictable; they're actually unavoidable. And if you're thinking of deploying a fleet of autonomous cars or robots, or a widely accessible AI model that people are going to use as an everyday tool, then it is almost certain that you are going to encounter, the system is going to encounter all of these rare, challenging situations. And what will make or break the safety of your system is precisely how it handles those rare situations. The way this is often joked about in the autonomous driving space is that, 99.9% of driving is really boring. Nothing's happening. You're just sitting there behind the wheel. Your autonomous car, you basically could just like do some naive sort of, adaptive cruise control and kind of just stay there and do nothing. And what could go wrong? The problem is that there's a tiny percentage of the time when it really matters whether you're making intelligent and appropriately responsive decisions. And so, in other words, being able to provide any sort of meaningful safety, not only safety guarantees, but also just in practice, empirically safe behavior, means that you need to be prepared to respond to these kinds of critical situations. I have a black swan here. Hopefully, folks are familiar with the meaning of this. The history of it is actually kind of interesting because it was initially the expression of a black swan meant something that doesn't exist. Ridiculous. Who could possibly think that's the black swan? That's another thing. Back in the day when folks in Europe weren't aware of the existence of black swan, which actually do exist in other parts of the world. So the modern meaning of the term is something that you may not think is going to exist, or you may not think you're going to encounter, but it very much could be there, and it is within the realm of possibility. And you may not be in a great place if you weren't ready to respond to it. So this is a hard problem. There's no denying it. But there are things that we can do to provide meaningful guarantees, and so I want to spend a bit of time talking about what we can do to actually have our autonomous systems, robotic systems, or as we said, more broadly, AI systems, ensure safety in this world that is fundamentally uncertain, where rare things can very much happen. All right, so the first the first thing that might come to mind is, well, can we just evaluate the autonomous system statistically? Just look at how often we encounter issues during testing, and try to obtain statistical confidence in the system's safety by doing a lot of testing. And this is something that makes good common sense, and is good engineering practice to provide statistical assessments. But it does have some limitations, and in particular, if you're sort of just trying to look sort of at your system as a black box and just analyze sort of end-to-end behavior, and just want to look at the big picture of the results, it can actually be really hard to ensure that it is really safe in to the statistical degree that you would need to really be sure that you can deploy the system. In particular, because as we said, these very, very hard situations are often very rare to find. So let me just give you a statistic that I think a lot of us tend to underestimate. Human drivers actually suffer one fatal accident on the road roughly every 100 million miles. This is in particular in the United States and other developed countries and Europe and so on. It's a similar number, which unfortunately becomes more frequent in developing countries where the infrastructure is not as smooth. However, this number is actually really low if you think about what this actually means. Now, it does add up to about 40,000 deaths every year in the United States alone, but that's just because we drive a lot. That's because there are many, many, many millions of miles driven every year in public roads. And another thing that I want to clarify is this across all roads and conditions. So this is not highway data. You go to sort of highway settings where you have sort of nicer, more organized infrastructure, you drop an order of magnitude in terms of the frequency. And this is worth keeping in mind because a lot of the autonomous driving testing that we do actually is in, highway-like settings. So, okay, a question that you might want to ask is, well, how much data do we need? Suppose that we develop a really, really robust autonomous driving technology and we want to get some statistical confidence that it is, say, at least as safe as human drivers by this metric, right? By the number of fatalities that they can expect to see every 100 million miles or every billion miles. So it turns out that this is something that researchers at RAND Corporation sort of went and worked out a while back in 2016. And I believe Kathy Wu, who is sitting here, was the person who first pointed me to this data that I think is really revealing, because what you find is that you actually need a lot of data. You need a lot of miles to get statistical confidence. And for example, to get sort of 95% confidence with 80% power for a fleet that is actually in reality 20% safer than human driving, meaning it has 20% less frequent fatal accidents. You need in the order of a little over 10 billion miles. Now, I have a question. I want to sort of get a sense from you. How long do you think? So Waymo has a fleet of, at least as of a few months ago, about 100 vehicles, sort of at any given time of day. There's on average 100 vehicles running around San Francisco. How long do you think it would take that fleet of 100 vehicles to collect the amount of data that you would need to get this kind of confidence that the fleet is safe?
100 years.
100 years. Oh, I hope it's not 100 years, because that would probably take too long. Any other guesses? But who knows? Maybe you're in the right order of magnitude. Anyone else? Anyone more optimistic or anyone more pessimistic?
1,000 years.
Okay.
The assumption that there would be more added as time goes on, like the more cars added.
Well, yeah. So you can say, oh, maybe over time we're gonna have more cars added as we start the game. Maybe some cars. Maybe at some point we're like, I don't know, 80% sure that it's safe enough, so we will increase the size of the fleet. It's kind of, before you have enough confidence, you're kind of taking a risk. You can argue that the fleets will grow, but you probably don't want to grow them too fast if you're not sure they're safe. But assuming that the fleet size is constant, the actual amount of time would be 500 years. So kind of, you were hitting sort of the right, you're bounding the order of magnitude. So that's not very practical. This, by the way, is assuming that you do a code freeze and you do no updates to your fleet in the meantime, right? Because you have to hold the conditions constant. So this is, I think it's clear that this is not going to work in this sort of naive form. Not to say that statistical information is not useful. It's just not going to cut it by itself. We can't just do this black box analysis and expect that this is how we're going to get our confidence. I don't think any autonomous driving company is going to want to wait for 5 centuries before we allow them to deploy this technology. So, but also, I don't think we need to say, no, it's fine, then forget about it. We don't need confidence in your system's safety, right? So then what do we do? Given that it's really hard. So there's this scene that I really enjoyed from the recent Oppenheimer movie, where Oppenheimer and the major in charge of the Manhattan Project are having this conversation about the possibility that the nuclear explosion might trigger a chain reaction that would actually propagate through the whole planet and destroy the world. So, they're having this conversation. Are you saying that there's a chance that when we push that button, we destroy the world? And Oppenheimer's response sort of gets summarized as, well, the chances are near zero. To which the major responds, near zero? And, Oppenheimer says, well, I'm a theoretician. What do you want from theory alone? And the major just says 0 would be nice. So, yeah, I think that the story here is we really would like to have something a little bit more informative than just a number that looks very small and that we don't necessarily fully understand, or that we're not necessarily even that sure about, when we're trying to understand whether a technology is safe. And the good news is that there are other tools that we can use that are complementary to statistical analysis that can allow us to give a more qualitative characterization of the safety of a system, where we can say, well, are there certain conditions or certain assumptions under which the system cannot fail? Can we come up with a set of hypotheses based upon which we can have a theorem, sort of, an if-then statement that if these conditions hold, then the system will not fail in a certain way that we have to find. And so that allows us to think of safety as a social contract, which I think is a very useful way to operationalize our safety sort of requirements and our demands as a society. So the idea then is that the autonomous system is going to actively guarantee safety under what is sometimes referred to in the autonomous driving industry, and we sort of are taking that term and trying to extrapolate it and operationalize it, and sort of give it a concrete mathematical definition of an operational design domain, or an ODD for short. And what this means, if you go and look at some of the modern automotive standards that are trying to put some definitions on top of autonomous driving, is it's a set of conditions under which an autonomous system is required to operate correctly and safely. And the idea is then that you just do not deploy the system out of those conditions, or if the conditions change and suddenly the vehicle finds itself outside of its operational design domain, then it needs to safely come to a stop, and it will not continue operating autonomously until conditions resume. So we try to take this sort of general definition in words and look at it from the perspective of dynamical systems and control and sort of, intelligent decision making. You can write an MDP or POMDP definition if you want. We're going to, for now, write it in the language of dynamical systems and control. So this means that there's going to be some state of the world that is going to evolve according to some, possibly structured model of for example, accounting for the laws of physics, in the case of driving, Newtonian dynamics or Lagrangian dynamics. And it could be uncertain. We don't necessarily say this is exactly how the world is going to evolve. We allow for some error in our model, for some uncertainty in our model, and we capture that with this last term, right? So in control systems notation, X represents the state of the world, T is the time index. We're going to be thinking in discrete time. So at the next time step, the state will be some function of the previous state, maybe at the present time, the control action U that's being taken by the autonomous system at the present time, and then this external influence that we don't know ahead of time, or we don't have control over, which you can think of as a disturbance term D, or just some general domain parameter D that determines the realization of our uncertainty. And so that uncertain environment realization, which by the way could include the behavior of other agents in the scene, for example, other road users, can be thought of over time as just the realization that we had at the first time step, the second time step, and so on. And often we don't have a perfect sensing of the state, so we can also incorporate some kind of measurement model where the measurement that we make at each time step is some other function h of the state and action that we take, and it could also be affected by how things get realized. So we can also allow for some uncertainty in the model. To avoid introducing a lot of terms, we can just pretend that we put everything in the same vector D. So now we have this uncertain model of both dynamics and perception. This is often referred to as model uncertainty and state uncertainty, or predictive and perceptual uncertainty. Yes?
Because when you use the word guarantee,
Yes.
I first interpreted it with something as a certainty that it would never happen. But that seemed rather strict. And particularly given you're having some uncertainty as one of the inputs.
That's right.
I would think you would need to define guarantee as with some probability, and it's often with service agreements that companies make. It tends to have a probability to it.
Right. Well, so-
99, some whatever percentile you want to
Mhm.
give. So are you trying to think of it in a deterministic way?
No, but that's a great question, right? So I think that there's often this. I think sometimes it's kind of viewed as this dichotomy, like either things are deterministic or they are probabilistic when there's an uncertainty. But actually, probability is not the only way to quantify uncertainty in a mathematical and sort of in a rigorous way. And so what we're doing here is, you're absolutely right that any meaningful guarantee needs to account for uncertainty. Unless you just happen to have a system that is so simple that you have a perfect model of the system, which is kind of just never the case. So here, the guarantees absolutely account for uncertainty. In fact, as you can, we explicitly say, hey, there's uncertainty over here. So the guarantees are not going to say, for example, this car can never crash. Rather, they're going to say, under this set of conditions, this car can never crash. Now, the formulation that we use is actually called non-deterministic uncertainty. It's not a term that I love because it's just telling you that it's not deterministic, and technically probabilistic uncertainty is also not deterministic. But what this formulation of uncertainty does is you can think of it as, it uses the support of the distribution agnostically to how the probability mass is distributed across that support. Or perhaps put more simply, it uses sets instead of probability measures.
Yeah, there was a fellow, Fred Schweppe at MIT, developed a theory, just as you're describing, where the uncertain was captured as unknown but bounded.
That's exactly, and so this is exactly the model that is being used here. And there is a line of work, not so commonly, I mean, somewhat commonly used, but not perhaps as commonly used as probabilistic uncertainty in sort of modern robotics that follows that approach. This is also referred to as robust uncertainty, which I think is a better term. And so, all or much of robust control theory is sort of based on this framework to quantify your uncertainty. So exactly following on the point that you're bringing up, the way in which we're then characterizing the uncertainty is by bounding the set of possible worlds or the set of possible conditions that might arise during the operation of the system. And so we're not going to be, for the purposes of safety, we're not going to be distinguishing what is likely to happen or what is unlikely to happen. We're only going to distinguish between situations that we are including in our operational design domain and situations that we are excluding from the operational design domain. And an important nuance here is that we're not saying that these things cannot happen. We're saying that we're not considering these things within the domain, meaning that if they happen, the system has no guarantees over those cases. And there needs to then be, I'm going to come back to the social contract in a moment, there needs to be some negotiation, some discussion between the developers of the technology and then, the society, the social decision makers who will then say, hey, that's not actually a reasonable assumption. We don't, if Waymo comes to us and says, we can guarantee that the car will maintain safety as long as it is the only road user for a 1 mile radius. That's just that's not an acceptable assumption. But on the other hand, you can imagine how it is not realistic to expect any autonomous driving company to guarantee that no matter what everybody else does on the road, the vehicle will maintain safety. Because of course, it's kind of provably impossible. You can easily come up with a counterexample where every road user simultaneously gangs up on your autonomous car to force it to collide. And that's also not very useful, right? To say like, well, the system is not safe in those scenarios. Sure. But then the question is, where can we draw a meaningful boundary, a meaningful line, so that the system can guarantee safety in a broad set of scenarios, while at the same time acknowledging that there are certain situations that are plausibly possible that it will not be able to handle, or at least that it may not be able to handle, right? If you have a situation that is outside of this domain and the vehicle handles it, then great, but there's a sense in which you just got lucky because we're not guaranteeing that. And so just to operationalize this a little bit more, the way in which we think about specifying an operational design domain, O, is as a tuple of three principal elements. Number one, the deployment conditions. So, are you going to turn on your autonomous car in the middle of a highway while driving at 80 miles per hour, or are you going to only allow it to get turned on maybe while it is in the garage or in some other kind of condition? Similarly for turning on a drone or deploying a language model. Number two, the set of possible realizations of the environment, right? Which you can think of the set of all possible sequences of D0, D1, D2 that you might encounter. So possible behaviors of other agents. Here's where you might be able to say, hey, I don't want to consider the case where everyone is simultaneously ganging up on me, but maybe I do want to allow one or two road users to simultaneously be acting in a way that is reckless or maybe even adversarial within a certain, within certain parameters. And then number three, very important, the set of failure conditions. Somebody has to tell us what is it that we cannot allow to happen, right? In the case of an autonomous car, this might be more straightforward, like make sure there are no collisions, or that you don't end up violating, the road boundaries or other sort of strict requirements we want to impose. In other robotic systems, it might actually be a subtle question. If you've got a caregiving robot, what are these failures that we want to make sure cannot happen? So again, it's not like every robot has an obvious operational design domain. There needs to be a conversation to establish what this domain should be. But given a domain, the wonderful thing about this is that there are tools, at least there are sort of there's a set of formal machinery that we can use to provide a guarantee that is now clear cut and has this very nice if-then structure, which is if you deploy the system from some allowed deployment condition and the environment's realization abides by what you have defined in your operational design domain, then the system will maintain safety. In other words, it'll satisfy the property that the state is never inside of the failure set. Sorry, I realize I'm pointing somewhere that most people probably cannot see. I'll just move over here. The state is outside of the set of failure conditions that you have defined for all future times. And so this kind of safety guarantee, if possible, I think can be extremely useful for a social contract because it gives us clarity. Then we can say, okay, this is now, it is clear to me under what conditions I could use the system. And by the way, this doesn't really differ much from the way we gain confidence, for example, for bridges. When some engineers go and say, oh, we're gonna build a bridge over here. The existing standards and the existing certification will require them to say, well, this bridge is built and certified for a maximum load of this many tons, and it can withstand an earthquake of this much magnitude. And of course, we're going to have a safety factor, build it so that it actually withstands a significantly stronger earthquake under a significantly larger load, so that we're completely confident that this system is not going to fail within its specified conditions. And note that it is important that we're not saying, well, this is a bridge that withstands 99% of earthquakes up to magnitude 7, right? I think that would kind of always make us a little bit uneasy, honestly, for many technologies that we do consider to be safety critical. All right, so back to why this is useful as an abstraction for the operational, for the social contract of safety. A really important condition here is that this operational design domain doesn't need to be static. We might start with something that is more restrictive and gradually allow the system to make more more assumptions, less restrictive assumptions. We might in other cases realize that we were missing some important cases that we did need to incorporate into our domain, and so we need to sort of make the assumptions less generous. And therefore, more the system will need to be safe in a larger domain. And so, a very important property of the way that operational design domain-based safety works is that if you have weaker structure or less world knowledge, this should make the system more conservative in order to maintain safety, but not less safe. In other words, if you say like, oh, actually, no, you have to account for the possibility that a cyclist might fall right in front of your car, which is actually another situation that happened during the time that I was at Waymo. You don't want the system to say like, well, I'm going to behave in exactly the same way as I was doing before I was considering that scenario. And so now, we'll see how it goes. Maybe we'll maintain safety, maybe we won't. No, when you incorporate that into the design domain, what might happen is the behavior of your system might need to change, become more conservative to be able to guarantee that safety will be maintained. For example, maybe what happens is you need to maintain, slightly larger distance with respect to cyclists because you're considering this possibility that before you were sort of allowed to neglect. All right, so let's jump a little bit into some concrete questions. I'm sure you want to not just have this be a philosophical discussion and actually see some concrete research. So the question that my group and I spend a lot of time thinking about is how can we actually generate these guarantees in a way that is tractable and that is also meaningful, that works for this definition of an OD, right? So we want to be able to take this sort of social contract that has been agreed upon by the self-driving company and the lawmakers and say, well, this is now how you synthesize the behavior of your system to make sure that it abides by this contract. And often you want the system to be able to carry out a range of different tasks within this domain, right? You've got a home robot, you define the safety conditions or the safety properties that it needs to have, but now sometimes you'll use it for helping you out with carrying the groceries. Other times you might need it to help you cook or make the bed, whatever it is that you have in mind. And so the safety analysis and the safety synthesis that we do should be general enough that it works under these different conditions. So we find that it's actually useful to introduce two different kind of separation principles. On the one hand, it is possible to synthesize the best effort safe behavior of the system in a way that perhaps lacks guarantees at the time of synthesizing it, but then use that to guide the verification of safe behaviors of the system, which we'll look at some examples of in a few moments. So we might use something like learning-based methods to construct these untrusted oracles that give us, pretty good recommendations in practice, but possibly wrong at times. And then we have some other method that could be model-based that actually checks in what cases we can rely on this recommendation. The other separation that we find is quite useful is separating the question of how do I keep my system safe and the question of how can my system do really well at this task that the user needs right now, right? In the case of driving, not crashing versus driving smoothly and getting me home on time. And so what we want to do here is avoid having to explicitly certify every possible task controller or task policy that the robot needs to use, like fetch me a coffee versus help me make the bed. If you have to certify that each of these policies that are going to be used for each task, each of them is safe, that's, there's going to be a lot more work. And so the question is, can we just take care of the safety once for the entire operational design domain, and then just make sure that whatever policy is used, whatever task is accomplished, will be done safely because we've already done the safety analysis for the domain. So turns out that something that allows us to exploit these two separation principles is this idea of safety filters. And so that's what I'm going to tell you about for the next 5 minutes or so. I realize that I've spent a lot of time talking about philosophy, so I'll have to keep it brief. And then we're going to look at how we can actually enable this kind of safety filter technology to also account for the fact that our autonomous system will be learning as it goes. It will be acquiring more information about other people's intent, about the conditions under which it's operating, and so on, during operation. And so safety can be more reliable and also less conservative if it accounts for the fact that I'm going to get more information as I go. But of course, it also becomes a more challenging and more interesting problem. And then finally, we're going to look at the way in which we can actively think about this idea of safety filtering as something that works not only for the robot, but really for the interaction between the robot and the human, and more generally between an AI system and the human. So let's jump in with the idea of safety filters. It turns out that a lot of the techniques that folks have been developing for safe robot decision-making, and in particular for safe learning in robotics over the last 10 or so years, can all be understood under a unifying framework, which is the idea of a safety filter, which, if you look at the number of papers that use these words, they've really spiked in the last couple of years. And it's because there's been a sort of maturing of the field where we now see that these different techniques have a common structure, and therefore that we can kind of exchange, sort of swap them out in a pre-interchangeable way. So a safety filter is any runtime process that is monitoring the operation of the autonomous system and that intervenes to prevent future failures. So the way this works, and sort of in a simple cartoon, is the robot gets some state observation. We're just going to call this X. And that is fed into a task policy. More generally, you could think of this as any kind of observation or sequence of observations. But some information is fed into the task policy, which then proposes an action. Instead of just applying that action directly, we're going to pass that action through an additional component, which is a safety filter, that also gets to look at the information available to the robot and then evaluates that action and decides whether that action is going to get us into trouble later on from the standpoint of safety. If the action is deemed safe, then it gets applied. But if it's deemed unsafe, it will get modified by the filter. This is why we call it a filter. It's kind of deciding what to let through and what to kind of tweak on its way out. A really nice property of doing this is that now, if you look at sort of the world seen by just the orange block, the task policy, you've just made it now so that the filtered system is safe under any task policy. So the task policy doesn't have to worry about safety anymore because you've given it a world that is sort of safe by construction. If your safety filter works, of course. And so this allows it to be quite general. Some really nice work that two of my PhD students, Jaime and Jaime, led about a year ago is this sort of unified theory that takes all the different safety filters and says, hey, can we find out what the common structure is, and can we write some common theorems that allow us to then kind of broadly prove that all of these systems work as long as they fit this sort of common set of conditions. And the idea is that every safety filter is really doing two functions. Number one, monitoring the action to determine if it's safe, if it's okay to take that action right now. And number two, intervening as needed to modify the action. And both of these steps are really informed explicitly or implicitly by this notion of, well, what would I do later on to maintain safety if it came down to it, right? So if things got complicated, what is my plan B for safety? We call that the fallback safety policy. So it turns out that a lot of techniques, essentially almost every technique that's been developed in the last few years to enable robots to make safe decisions, fall under this general sort of structure. And so I'm going to quickly sort of, I think this is just stating what I just said in words. So you want to first check if the action will allow you to still use the fallback plan B later, and if needed, you'll need to override. So the nice, a nice thing about this is that you can use the same structure to write this universal safety theorem that sort of slightly translating here into words. What it's saying is, if you're given an ODE tuple, then any safety filter that satisfies two key properties will actually maintain safety for any task policy that you're using to generate proposed actions. The first one is that it needs to be conservative, and this means that if the action proposed from this given state is deemed safe, which we indicate here by a classifier that says safety greater than 0, then it must indeed be true that the next state that is going to get you into is a state that is inside of the safe invariant set of your fallback policy, meaning the next state is one from which your policy, if you decide to call on it, your fallback policy, will maintain safety for any realization of your disturbance. And the second property is that your intervention scheme needs to be sound, which means that whatever you're using to intervene in the blue block should never choose an action that is deemed unsafe over an action that is available, that is deemed safe. So anytime that your fallback would be safe from the current state, then you're not going to accept the proposed task action if that one is not safe. All right, so that's all that this theorem is saying. And as long as these properties are true, then your safety filter works. And so it turns out that you can take Hamilton-Jacobi reachability analysis, control barrier functions, model predictive shielding, the classical simplex methods, all of these different techniques that come from different backgrounds, formal methods, control theory, robotics and motion planning, all of these satisfy these properties so that you can basically write this theorem with a few sort of footnotes in the form of corollaries and saying, by the way, all of these things maintain safety. This also allows you to, come up with a taxonomy of, how these different methods compare in terms of how they monitor and how they intervene, what kind of guarantees they can give and how you can synthesize it. I encourage you to check out the paper. This not a lot of time to talk about these, but I want to talk about one particular important observation here, which is that in principle, there is such a thing as the least restrictive safety filter that you could have. In other words, a safety filter that intervenes only when this is strictly necessary to maintain safety and in no other circumstance. And this is very useful because if you had such a safety filter, that would mean that you can take any policy you want. The policy will be allowed to do anything at once, any task, as long as it's safety. The only time when it's not going to be allowed to take an action is when taking that action would lead you to, at least in some version of your uncertainty, inevitably violate safety, which by definition, we don't want to allow. And so as we were discussing earlier, and Naveed and Ziyang have been doing some really nice work to show that you can actually get, you can learn an optimal solution to your reinforcement learning problem if you have access to such a filter, because there is no opportunity cost. There's nothing that you would have wished to do that this filter wasn't allowing you to do. And so a nice set of cases where this can work is when you have a robotic system where your dynamics are simple enough. So this is a drone where we're only considering vertical flight. So we're kind of cheating a bit. It's a 2D system, so it's kind of straightforward to compute the safety filter. And so what we did here is we just dropped the robot we turned it on in the middle of the room, and we said, hey, figure out how to fly. And the robot actually learned how to fly. Eventually it learned how to go up and down, which is what we wanted to do. And it never crashed. And the reason that it never crashed is that we had pre-computed a safety filter that said to the reinforcement learning algorithm, try out whatever you want, but if you do something that's going to make you crash, I'm not going to let you. I'm going to override. So, there's good mathematical understanding and also empirical evidence that these systems work incredibly well when the system is simple enough that you can go ahead and compute your maximal safe set, which results in the least restrictive safety envelope that you can filter your system for. If you're wondering what the rule looks like for the filter, it's very simple. It's just saying if you're inside of your safe set, do whatever you want. So phi returns you. And if you touch the boundary of the safe set, then we're going to override you right away to make sure that you stay inside of this envelope. Anyway, just in a nutshell, the problem with this is that you need to do dynamic programming to compute the optimal thing to do for safety. And this just really doesn't scale. I'm just going to share very quickly the way this kind of goes. So we can do this sort of analysis for things like a drone flying vertically, or maybe a planar vehicle model where you're just considering your vehicle's motion with a relatively simple set of dynamics. And this takes hours to days to compute and a few gigabytes of RAM. But the problem is that as soon as you start to try more complex systems like drones and aircraft, where you consider the full motion and so on, then it's going to start taking you weeks to years and terabytes of RAM. So somewhere in between here, you kind of reach the limit of numerical tractability.